Now I request Sri Jamas, HOD, Department of Physics, Maharajas College, to felicitate the program.
Thank you, Amrita. Thank you, Shiba teacher. Good afternoon, everybody. I am Srija, HOD of Physics, Maharajas College, Ernakulam. Today it is a happy moment for us. Actually, it is a privilege, prestigious moment for all of us because we have got an opportunity to co-host this interesting seminar organized by Kerala University Physics Department. We are all so happy and we are all thankful to all of you for providing us such an opportunity. On behalf of Department of Physics, Maharajas College and Directorate of Collegiate Education, I would like to express our sincere gratitude towards organizing such an eminent program for popularizing the works of veteran teacher Aruldhas sir and commemorate him during this particular scenario. And special congratulations to Dr. CBKS, HOD of Physics, and his efficient team for this particular effort. Let this program be a great success. We all wish this program to be beneficial for all the student community of this present scenario. Today we have Dr. Anand Narayanan, an eminent physicist, is here with us to deliver an interesting talk on finding the monster in the center of our galaxy. The title itself is so interesting. So definitely this talk will be beneficial for all the students and they will get enjoyed and motivated from this talk. I wish once again, I wish all success for this Aruldhas Memorial Lecture Series organized by University of Kerala Karivattam campus, and wish all the success for this program. Now let us enjoy this talk. Thank you, everybody.
Thank you. Thanks for, sorry. Amrita, continue.
Okay, sir. I'm sorry. We'll be having an introduction about the speaker. That's why I interrupted.
Okay. I'll wait. Yeah, go ahead.
Sorry, sir. The speaker for today is Dr. Anand Narayanan, sir, who is currently the Associate Professor of Department of Earth and Space Science, IISc Trivandrum. To introduce the speaker, I would like to call upon Srihari A. of 2nd MSc Physics, who is doing his project work under Anand, sir.
Okay, Amrita, thank you. Okay. Hope കേൾക്കാമെന്ന് വിചാരിക്കുന്നു. അമൃത പറഞ്ഞ പോലെ തന്നെ Anand sir currently Associate Professor of Department of Earth and Space Science, IISc Trivandrum. Talking about his qualifications, he got a BTech in Electrical and Electronics from College of Trivandrum, College of Engineering Trivandrum. Then later he's done in MS in Astronomy and Astrophysics, Pennsylvania State University. Then he's got a PhD in Astronomy and Astrophysics from the same university. Okay, his research area was the properties of diffuse gas in intergalactic medium and the regions of surrounding galaxies. സാറിന്റെ എക്സ്പീരിയൻസിനെ കുറിച്ച് പറയുകയാണെങ്കിൽ is a graduate researcher at Department of Astronomy and Astrophysics, Pennsylvania University. Then assistant scientist, Department of Astronomy, University of Wisconsin-Madison. And also currently he is associate professor of Department of Earth and Space Science, IISc Trivandrum. പേഴ്സണൽ എക്സ്പീരിയൻസ് വെക്കുകയാണെങ്കിൽ കഴിഞ്ഞ ഒരു വർഷമായിട്ട് സാറിനെ കുറിച്ച് അറിയാം. കോളേജിൽ മിനൂമിസ് ആണ് സാറിനെ എന്നെ ഇൻട്രൊഡ്യൂസ് ചെയ്തത്. പിന്നീട് IISc വെച്ച് പരിചയപ്പെടാൻ കഴിഞ്ഞു. സാറിന്റെ കീഴിലാണ് എൻ്റെ MSc പ്രോജക്റ്റ് ഞാൻ ചെയ്യുന്നത്. ഇതിനെക്കുറിച്ച് കുറച്ചും കൂടെ ഒരു പോയിന്റ് ആഡ് ചെയ്യുകയാണെങ്കിൽ, ട്രിവാൻഡ്രത്തൊരു ഒബ്സർവേറ്ററി ഉണ്ട്. ഒബ്സർവേറ്ററി അതിനെക്കുറിച്ച് സാറിൻ്റെ കീഴിലെ കുറച്ച് പേരും കൂടി ഒരു ഡോക്യുമെന്ററി ചെയ്തിട്ടുണ്ടായിരുന്നു. അങ്ങനെയുള്ള വർക്കുകളും സാറിനകത്ത് ഇതിനകത്തുണ്ട്. യൂട്യൂബിൽ വന്നിട്ടുണ്ടോ എന്ന് എനിക്കറിയത്തില്ല, അടുത്ത് തന്നെ പ്രതീക്ഷിക്കാം. ഓക്കെ, അധികം സമയം കളയാണ്ട് തന്നെ നമുക്ക് ടോക്കിലേക്ക് കടക്കാം. ലെറ്റ്സ് ഇൻവൈറ്റ് അൻസാർ ഫോർ ദി ടോക്ക്. ഓവർ ടു യു, സർ.
Thank you, Srihari. Good afternoon, everyone. Thank you, Srihari. Thank you, Amrita, for that generous, detailed introduction. Thanks to the Department of Physics of Maharajas College and the Physics Department of University of Kerala for inviting me to give this presentation. It's truly a great honor for me to be able to give this lecture, which is done in memory of a distinguished researcher, a very, very popular teacher, a mentor for many people, and a person who has had a profound influence in the Physics Department of University of Kerala, Professor G. Aruldhas. I have not had the privilege to know Sir personally, but I know him through the half a dozen textbooks that he has written on various aspects of physics. These textbooks continue to be a great resource for many students. So it's something of great honor for me. And I would also like to thank Dr. Sibi for this opportunity. Sibi sir is a great friend, and Srihari just mentioned about the documentary film on the Travancore Observatory. That documentary was made possible because of the help and support from Dr. Sibi sir and the other faculty members in the Department of Physics of University of Kerala, Kalivattam. So our friendship goes a long way now. Okay, so I'll start the presentation. I'll start sharing my slides, and before I go into this presentation, I just want to add that my internet is connected through my phone. So during the presentation, if a phone call comes, the internet connectivity may be disrupted for a few seconds, but I will quickly reconnect. Okay. Okay, is the screen visible to all?
Yes.
Yeah, thank you. So the context of today's presentation is the 2020 Nobel Prize in Physics, which was announced last month on October 6th. As most of you know by now, the 2020 Nobel Prize in Physics was awarded to 3 people who work in the field of astrophysics. One is, of course, the famous Sir Roger Penrose. Penrose was awarded 1/2 of the Nobel Prize in Physics for his lifetime work, where he showed that black holes, or rather black hole singularities, are an inevitable consequence of the principles of general relativity. When you have a large amount of mass concentrated into a tiny volume, the warping of space is so severe that nothing, not even light, can escape from it. So within the mathematical framework of general relativity, Penrose was able to show the existence of black hole singularities. The other half of the Nobel Prize was shared by Reinhard Genzel and Andrea Ghez. Both of them are leaders of 2 separate teams of astronomers. The European team, which is led by Reinhard Genzel, who is currently the co-director of the Max Planck Institute in Garching, Germany, and the US team led by Andrea Ghez, who is a professor at the University of California, Los Angeles in the US. Both teams headed by Reinhard Genzel and Andrea Ghez, they spent nearly 3 decades, close to 30 years, painstakingly studying the center of the Milky Way galaxy, and their collective work has provided one of the most definitive pieces of evidence for the existence of a supermassive black hole in the center of our galaxy. So when I say supermassive black hole, what I mean is a black hole with a mass that's more than 4 million times the mass of the sun. So in today's presentation, I'll be exclusively focusing on the work of Reinhard Genzel and Andrea Ghez. Their work is a triumph of observations of very fine measurements, which was made possible because of some great advancements that happened in the field of optical engineering, which helped astronomers to manipulate light in very interesting ways. So I'll be going over these aspects in my presentation. So before getting into the details of the discovery that led to the Nobel Prize, I will try to set the context for this presentation. Okay? And to do that, we need to rewind back in time to the early 1900s. Okay? So the beginning of the 20th century. This is the time when astronomers were just beginning to map, okay, just beginning to understand what the overall shape and structure of our Milky Way galaxy is. So the question is, how did astronomers find out that our galaxy has a center? Okay. And how did they find out that we are not at the center? By we, what I mean is the solar system is not at the center of our galaxy. How did astronomers come to that realization? And lastly, if we are not at the center of our galaxy, then the obvious question is, what is at the center of the Milky Way galaxy? So how did astronomers find out that? So we will go over these aspects, which will set the context for discussing the 2020 Nobel Prize in Physics. Okay. Now, as it turns out, knowing the shape and size of Milky Way galaxy, of our galaxy, and knowing our own place within the galaxy, these are really difficult problems. And the reason for that is that we are inside the galaxy. Okay? We are embedded within the galaxy, and from where we are, it's extremely difficult to get an overall idea of how the rest of the galaxy looks like. The best analogy that one can use for that is, imagine that you are stuck inside your home. Okay? You have never had the chance to go out of your home. Okay? So you are stuck inside your room, and somebody were to give you a paper and pencil, and if they asked you to draw the architecture of your house, okay, how your house looks from outside, it will be very difficult for you to do it because you have never seen your house from outside. So, but what you can do, that doesn't mean that you cannot make an inference of what your house looks like. What you can do is you can actually do measurements sitting inside the house. You can try to look towards your left and towards your right and see how far away the walls are. You can look towards the front, you can look towards the back, you can look above and you can look below and see how things are organized around you. And more importantly, you through the windows of your house, you can look into the outside world. You can see other buildings and you can try to see what shapes and sizes those buildings have. Using all these measurements, by putting all these measurements together, you can map out the architectural layout of your own house, okay, to some level of precision. And that's exactly what astronomers also did. Okay, it's impossible for us to travel outside of our galaxy because the galaxy is enormously large. So what astronomers did is they counted stars, and not just stars, but gas clouds and dust in the interstellar medium of our galaxy. So through very careful measurements, astronomers started mapping the position of stars, star clusters, interstellar medium, and interstellar gas and interstellar dust within our galaxy. And they looked at how all these ingredients that belong to our galaxy, how they are distributed in the sky. And they also took images of other galaxies beyond the Milky Way, and based on all that, they inferred what the galaxy looks like. So I'll go through some of these observations which they did. Okay. So in the next slide, what you are going to see is a visualization which is based on real data. What you will be seeing is what astronomers refer to as a star count map. Okay. This particular map is taken from the 2MAS survey. 2MAS stands for 2 Micron All Sky Survey, which is an astronomical survey of the entire sky at infrared wavelengths. And the animation that you're going to watch, it shows how stars, point sources, which are stars, how they are distributed in the night sky from the very bright stars to the very faint stars. So I just play this animation here. And this number changing indicates that we are going from bright stars to fainter and fainter and fainter brightness levels. You can see that as the brightness level goes down, the number of dots in the plot is increasing. That is just to indicate that the number of stars is increasing, because at any given because at any given patch of the sky, there are very large number of faint stars compared to brighter stars. So if you were to look at the distribution of point sources in the sky like this, you will see that the stars are not uniformly distributed. Most of the stars seem to be distributed along a disk like this, with fewer stars above and below the disk. So this is telling us that our galaxy has a planar geometry. It is like a disk rather than like a sphere. If it was like a sphere, then the distribution of stars should have been uniform across the sky, but it is not. Okay? So measurements like these tell us that our galaxy is a disk galaxy. Now the question is, does this disk galaxy have a morphological center? Does it have a center that we can point at? Okay. So again, an analogy is useful. Okay, suppose you are walking into a crowd of people, and there's a crowd that is gathered, and if you want to know who is the center of attraction, all you have to do is take a few steps backwards and look at how the crowd is distributed. Okay. If there is a center of attraction for that crowd, then obviously the entire crowd will be arranged around that center of attraction, okay, of the crowd. And so this is exactly the kind of measurements that astronomers also did. They looked at the distribution of objects in the sky, and they tried to see whether the objects in the sky are preferentially distributed with respect to a certain point. If they are not preferentially distributed, if they are just randomly distributed within the disk, then it means that our galaxy is a disk galaxy with no morphological center. If the objects are preferentially distributed around the solar system, then that means we are the center of our galaxy. But if they are distributed around some other point, then some other point is the center of our galaxy. Okay. So the question is, does this galaxy, which has a disk-like morphology, does it have a center? Okay. In other words, are the objects belonging to the galaxy distributed around a certain region? Now, to understand these set of observations, we again have to go back to the early 1900s, specifically to the year 1914. This is Harlow Safely. He was the head of Harvard College Observatory, and Safely, back in early 1914, he began an observational campaign to study large groups of stars called globular clusters in the sky. So I'll show what we call a star cluster, specifically a globular cluster. Globular clusters are star clusters with anywhere from 10,000 to 1,000,000 stars confined to a region that is roughly 20 to 100 light years across. Okay. So there's a huge concentration of stars, and there are a large number of globular clusters that are present within our galaxy. So what Safely did is, using the one of the largest telescopes which was available to Safely back in the early 1900s, which is the Mount Wilson Observatory in California. The telescope's picture is shown here. Using this telescope, Safely started measuring the distances to these globular clusters. Okay. So he, to the best possible accuracy, he started estimating the distances to all the known globular clusters within the Milky Way galaxy. And he also mapped out their position in the sky. So he had information on where they are positioned in the sky. He also had information on how far away they are from us. And with this, he plotted the distribution of globular clusters. And the distribution looked like this. So this is along the x-axis is distance in units of kiloparsec. Okay? So kilo means 1,000. Parsec is a unit that astronomers use to talk about distances between objects. 1 parsec is approximately 3.2 light years. Okay. So it's more than a light year. So kiloparsec means 1,000 parsec. So this is 10,000 parsec, 20,000 parsec, 30,000 parsec, etc. And this is the other direction. This horizontal line at 0, this corresponds to the disk of our galaxy. Remember that I already showed you that our galaxy has a disk-like structure. So this corresponds to the disk. This is distances above the disk. This is distances. These are distances below the disk. And the red dot represents the solar system. Okay. So we have Safely chose the solar system as the reference because we are going around the sun. We are part of the solar system. So it's an obvious choice for defining the 0, 0 coordinate of this reference. So this is the solar system, and every black dot that you see is the location of a globular cluster within the Milky Way galaxy. So this is how safely determined the distance, and this is the version of the plot back from the 1918. And as it turns out, the distances that Harlow safely had estimated to many of these globular clusters had huge uncertainties because of some observational difficulties. And now we can do the same set of measurements with much better precision. And if you do the same set of measurements, this is an updated version of the 1918 plot, you will find that the globular cluster distribution is much more concentrated. Okay? And the reason is not because the globular clusters have moved in their position from 1918 to 1999. It's because the distances that safely had estimated to these globular clusters, many of them were not accurate enough. Okay? So this is an updated version. And you can immediately see that the globular clusters are not distributed around us. These star clusters are not distributed around us, which means that even if our galaxy has a center, we are certainly not at the center. Okay, we are displaced by about 8,000 parsec from the center of our galaxy. Okay, at some point, that is roughly 8,000 parsec from the center of our galaxy. That's 8 kiloparsec, and it is around that point that all the globular clusters seem to be preferentially distributed. So these observations from Harlow safely that started off in 1914, and the observations got over in 1919. During that time period, safely was able to show that our Milky Way galaxy has a morphological center, and we are not at the center. We are displaced from the center by roughly 8,000 parsec. Okay. So after safely, there have been many groups who have tried to estimate the distances to the center of our Milky Way galaxy using more or less the same approach as what safely had, measuring distances to star clusters. So this table shows attempts from many different groups to measure the distance to the center of our galaxy, and you can see that the values more or less agree with each other. It's all roughly around 8.3 or 8.5 kiloparsec. So that is 8.5 into 1,000 parsec. And here are the measurements to the distance to the center of our galaxy by Andrea Gess's group, the US group, and Reinhard Genzel's European group. Okay, from two papers that were published in 2008 and 2009. And you can see a remarkable agreement between their distance estimations to the center of our galaxy. So the bottom line is, by mapping the distribution of star clusters, we now know that there is a center to our Milky Way galaxy, and we are not at the center. We are displaced from the center by about 8.3 kiloparsec. So the obvious question is, if we are not at the center, then what is at the center? Is there something interesting that is present in the center of the Milky Way galaxy? So before we go into that, okay, this is just an overall anatomy of how our Milky Way galaxy looks like. If you could travel outside of the Milky Way and look at it from above, we would see that our galaxy is a disk galaxy with spiral structure to it. We are not at the center. We are about 2/3 the distance from the center, roughly 30,000 light years from the center of our galaxy. If you were to look at our galaxy edge-on, we can see that it's almost a disk. And with all the globular clusters distributed around the center. So what is at the galactic center? That's the obvious question. So that is what we are going to get into, and that automatically leads to Reinhard Genzel and Andrea Gess's work. Now, if you are doing stargazing during the months of September, October, etc. For example, if this month you were to go out and look at the night sky, you are likely to spot a zodiacal constellation called Sagittarius. Okay? You have to look in the southwestern part of the sky. I think by around 10 p.m. or so, the constellation becomes very low in the sky, very close to the horizon, so it may not be possible to see. But around 9 p.m. or so, if you go out, you may be able to spot the constellation Sagittarius in the sky. And the Sagittarius is important because the center of the Milky Way galaxy lies in the direction of the constellation Sagittarius. So if you are looking at Sagittarius constellation, you are actually looking towards the heart of the Milky Way galaxy. Now, it's very difficult to observe anything at the galactic center at visible wavelengths of the electromagnetic spectrum. That's not because our telescopes are not good enough, and the reason why it's very difficult to look to see anything that's present in the galactic center is because if you're looking towards the center of our galaxy, your line of sight intercepts with huge columns of gas and dust, interstellar gas and dust, that is present between us and the center of the galaxy. These huge columns of gas and dust, they block our view into the galactic center. The gas and dust would scatter off the starlight that is coming to us from stars which are present close to the galactic center. The dust scatters it off. So, because the center of our Milky Way galaxy lies in the constellation, lies in the direction of constellation Sagittarius, it's a very favorite patch of the sky for astrophotographers. So, I will show you some photographs that members of the Amateur Astronomy Club here in Trivandrum took of the Sagittarius constellation looking in the towards the center of our Milky Way galaxy. So this is a photograph that was taken by an alumni of University of Kerala Department of Physics, Srirag. He is currently doing PhD at IISER Trivandrum. He took this photo from IISER Trivandrum. This photograph was taken with a DSLR camera by looking in the direction of the constellation Sagittarius, and you can see that there are countless untold number of stars in this image, but along with that you also see this dark band which is running across the image. This dark band corresponds to huge columns of gas and dust which is part of the Milky Way's interstellar medium, and this gas and dust is present along the disk of the galaxy, which makes observations towards the galactic center very difficult, because whatever is present on the other side of this column of gas and dust, it is obscured from our view because of the light getting scattered off by this dark columns of gas and dust. I'll show you one more picture. This is taken by, again, members of the Amateur Astronomy Club, Fahad Hasis and Kiran Mohan. Both of them are scientists at VSSC. They are also very much into astrophotography. And here again in this picture, you're looking in the direction of the constellation Sagittarius. And once again, you can see this dark columns of gas and dust. So since the dust scatters the light that is reaching us from the center of the Milky Way galaxy like a thick curtain, okay, what astronomers have been doing is they have been trying to look outside of the visible wavelength region, primarily in the infrared and X-rays, to peer into the center of the galaxy, to see through this gas and dust. So what I will do next is I will show you some wide field images of the galactic center taken at infrared and X-ray wavelengths. So this is a composite of near-infrared image taken by the Hubble Space Telescope and an infrared image taken by the Spitzer Space Telescope. Both are space telescopes. Spitzer is optimized to look at the universe at infrared wavelengths. Hubble Space Telescope can observe the universe at visible wavelengths and infrared. So this is a composite of infrared images from HST and the Spitzer Space Telescope. It's a mosaic, which means that many small snapshots have been stitched together and you are looking towards the center of our galaxy. The image is false color to highlight the stars and dust properly, and near-infrared wavelength is a very popular region of the electromagnetic spectrum for observing the galactic center, because near-infrared photons, because of their large wavelength, they are able to pass through the dust in the Milky Way's disk, and it can show us what is present in the central regions of the galaxy. And we see that there is a large concentration of stars which are present towards the central regions of our galaxy. Now, this particular image is again looking at the galactic center, but not at infrared, but at radio wavelengths. Okay, so long wavelengths. And so this is a radio image of the central regions of the galaxy. Again, this is a false color image. Okay, we cannot see photons of radio wavelength. So what astronomers do is they measure the intensity of radio emission and they convert it into visible intensity so that we can look at it in a photograph like this. This image covers roughly 4 degree by 5 degree in the plane of the sky, and that's roughly the size of about 10 full moons. Okay, so that's how big a region we are looking at. And as you can see at radio wavelengths, when you look at this image, you see a lot of bright regions That means that these regions are bright at radio wavelengths. Many of them are supernova remnants. Supernova remnants means they are remains of stars that exploded thousands to millions of years ago, and they are all present very close to the galactic center. So here is one supernova remnant, here is another one, and whatever is marked as SNR corresponds to the remains of a star that lived and died long ago. They are all supernova remnants. But what is of importance to us is this bright object over here, which has been marked Sagittarius A star. Okay? So this is of particular importance to us. Sagittarius A star is a very persistent and very bright synchrotron radio source. And it was known back in the 1970s itself that the center of the galaxy coincides with Sagittarius A star, which means whatever is present in the center of our galaxy, it is embedded within the Sagittarius A star. So the Sagittarius A star is therefore a favorite region of astronomers who study the activity associated with the central regions of our galaxy. I'll show you one more image of the central regions of the galaxy, not an infrared or radio, but an X-ray wavelengths. So this is again a mosaic of X-ray images of the central regions of the galaxy taken by the Chandra X-ray Observatory. Again, it's a false color image. You're looking at a region that's 900 light years by 400 light years across, centered on the Sagittarius A star region. So this bright plume that you see over here, this greenish plume of diffuse glow that you see, that is Sagittarius A star. So since it's so bright, it's clearly telling us that there is a lot of hot gas that is present, because only hot gas can emit strongly at X-ray wavelengths. It's a diffuse haze, and the temperature, based on the intensity of X-ray photons that we receive, one can estimate the temperature of the gas in this region, and the temperature roughly comes out to be about 10 million Kelvin. Okay? So whatever is in the center of our Milky Way galaxy, it lies embedded within this hot plume of plasma with temperature of roughly 10 million Kelvin. And this region is not just bright in visible wavelength, it's bright in infrared wavelengths, it's bright in radio wavelengths, it's also bright in X-ray wavelengths. Okay? So these kind of multi-wavelength observations, they have been going on for many years now, and all of them show that the galactic center is a very crowded region with a lot of activity that's going on. And what Reinhard Genzel and Andrea Ghez, what their teams did was to look through this crowded region of gas and dust. They picked out stars that are very close to the galactic center. It's very difficult to pick out individual stars that are very close to the galactic center. It requires very careful observations. So they, through very meticulous observations, they picked out individual stars that are very close to the center of the galaxy, and they monitored their movement, how they are moving over long periods of time. And based on that, they determine what could be the mass of the object at the galactic center that these stars are going around. Okay, so that is essentially what the observations constituted. Okay. So how does the movement of stars, how does it tell us about the mass of the object at the galactic center? So the idea is very simple. Okay. There are equations that govern the motion of objects under the influence of gravity. You all know those equations. So let's say that the sun, we have the sun and the planets going around it. Let's say that the sun stops emitting light. Okay, for a moment, let's say that the sun is not luminous anymore, but it still has a lot of mass. So the planets will continue to revolve around the sun because the gravitational force still exists. So if you now measure the orbits of any of these planets, one or more of these planets, if you determine how far away they are from the point around which they are revolving, and how fast they are moving, meaning how long does it take for these planets to complete their one orbit around the center, then even if you cannot see the sun, you can estimate what is the mass of the central object around which these planets are revolving. And the idea is essentially Kepler's third law. Okay? If you know how long it takes for these objects to go around the central object, and if you know how far away they are from the central object, then you can determine what is the mass of the central object. More accurately, what is the mass enclosed within this radius? That is what you can determine. Okay. So this is exactly what Reinhard Genzel and Andrea Ghez did. Okay, they measured the positions and velocities of stars that are very close to the galactic center, and using those measurements, they estimated what is the mass of the invisible object that is present in the center of our galaxy. So the approach is follow the kinematics of stars close to the galactic center and use that to determine the mass and size of the object in the galactic center. And as I already told you, it's best to do these observations at infrared wavelengths, because in visible wavelength, the light is extinguished by the interstellar gas and dust that is present between us and the central regions of the galaxy. So the question is, how does one go about measuring velocities of objects, velocities of stars? Now, any velocity in 3D space can be decomposed into two components. One is a component of velocity that is directed towards us or away from us, which is the radial component. And the other is the velocity that is perpendicular to our line of sight, which is the transverse component or the tangential component. So if you have a star that is moving in the sky with a three-dimensional velocity, you can break the velocity into the radial and the transverse component. If you measure the radial component and if you measure the transverse component, then you can estimate what the velocity of that object is. Okay, and with that you can reconstruct the orbit that that particular star is moving around. So how does one measure the tangential velocities of stars? Okay, so what I mean by tangential velocity is, if you are an observer and if you are looking at a star like this, the star may be moving across the plane of the sky. Okay, so initially its position may be here. If you observe it after some time, its position may be here. So this may correspond to an angular displacement in the plane of the sky. And if you know how much time it took for the star to move from here to here, then you have the time and you have the angular displacement. With the angular displacement and with the time, you can calculate what the angular velocity is. In astronomy, this is referred to as proper motion. And once we have the angular velocity, if you know how far away the star is, okay, then we can convert that angular velocity into a linear velocity. It's basically V is equal to omega into R. Okay, V is equal to R omega, that expression. This is angular velocity. This is the distance to that object, okay, which is moving. Now, the only difficulty, this appears to be a very simple thing to do, but the only difficulty is these stars, which are close to the galactic center, they are at distances of 8,000 light years from us. That means that even if the star is moving at a large speed, the distance is so large that the angular displacement will be very, very small. Even if the star were to move a large distance, the angular displacement corresponding to that linear displacement will be very small because of the enormously large distance that separates us from those stars. So typically, the angular displacement is of the order of milliarc second over a time frame of 1 year or so, okay, which is very, very small. So just to remind you how tiny milliarc second is, I'm sure all of you have seen a protractor. Okay, the angular interval between any two tick marks is roughly 1 degree, and arc second is 1 by 3,600 of that, and a milliarc second is 1 by 1,000 of that arc second. Okay, that is how much the positions of stars would shift in the plane of the sky, even if they were to move at enormously large speeds. Okay, because these stars are at large distances from us. So this means that to be able to track the movement of these stars, you have to continue observing them for long periods of time. You cannot finish the project in 2 months or 3 months. You have to do this set of observations for years and decades. Only then you will see a sizable, only then you will be able to map out a sizable trajectory for this star. And the second is, you should be able to measure the position as accurately as possible, because the changes in position that you're measuring is very, very small. So if the position of the star is not known precisely, then you will not be able to measure small changes in position. Now this measuring the exact positions of stars is extremely challenging when we are trying to do it with the help of observatories on Earth. And the reason is because Earth has a dense atmosphere around it, and this atmosphere is never stationary. Okay, it's always turbulent, and the turbulence in the Earth's atmosphere, it limits the performance of ground-based astronomical telescopes. The turbulence causes the stars to twinkle, it distorts and blurs the images. And this is a source of great frustration for astronomers because it limits the angular resolution of the images that we take. The distant stars will appear as point sources, and because this light from these distant stars, as it passes through the Earth's atmosphere, the atmosphere has many layers of gas with different densities, temperatures, and chemical composition. That means that the index of refraction, the refractive index, will be different in the different layers of gas in the Earth's atmosphere. So a ray of light that is coming from a source at infinity, as it enters the Earth's atmosphere, it gets refracted multiple times. So what happens is, on the focal plane of the telescope, so let's say that this is the focal plane of the telescope. On the focal plane of the telescope, the image will keep jumping around. And the turbulence of the atmosphere, it changes every millisecond or so. That means that if you're taking a picture with an exposure time of 10 seconds, in that 10 seconds, if the atmospheric turbulence is changing every millisecond, then in that 10-second exposure, the position of the star in the detector plane will shift 10,000 times. So at the end of the 10-second exposure, instead of seeing a point source, all we would see would be a very blurred image of that star. Okay. So this is a serious limitation. Okay. So just to illustrate how bad the situation is when we try to look at the universe through the Earth's atmosphere. So here is a picture of a certain patch of the sky taken by a space-based observatory. All the dots that you see, they all correspond to stars. And here is a picture of that same patch of the sky taken by a ground-based telescope. You can see that instead of seeing these small points, which are all stars, all you end up seeing are blurred images. And this is because of the turbulence of the Earth's atmosphere blurring out the signal. Now, so this limits the resolution. So let's say that any one of them is a star that is close to the galactic center. And if the images are blurred, then you will not be able to measure tiny changes in the positions of these stars of the order of milliarcsecond or so over the time frame of a few years. So somehow we have to improve the image quality, and only if we can improve the quality of the images will we be able to measure small angular displacements in the positions of the stars in the sky. Now, interestingly, there is you cannot always do these observations from space. Okay, so one can always say that, okay, why don't we use such a space-based observatory like the Hubble Space Telescope to do it? The problem is that Hubble Space Telescope is a costly instrument. There are many astronomers who are trying to do different kinds of observations using the Hubble Space Telescope or the Spitzer Space Telescope or the Chandra X-ray Observatory. So if you cannot always get a lot of time, observing time on a space-based telescope, your science idea has to be competitive enough to be awarded time, and that also you will get only small amounts of time on these space-based observatories. So you have to somehow come up with ways to improve the imaging capabilities of ground-based telescopes. And interestingly, there is at least one way to compensate for the distortion of images due to the atmosphere, and that is with the help of something called adaptive optics. Okay. Some of you may be knowing about adaptive optics already, but since adaptive optics is central to this entire discovery that was awarded the Nobel Prize, I'll spend the next 5 minutes explaining what adaptive optics is. It's essential aspects of adaptive optics. So adaptive optics is a technology that can correct in nearly real time the blurring caused by the turbulence in the Earth's atmosphere. And this idea is not new. Theoretically, the idea of adaptive optics was put forth back in the 1950s itself by a person called Horace Babcock, who was an astronomer working at the Mount Wilson and Palomar observatories. But however, in 1950s, the technology was not ready to deal with the kind of exact requirements which is needed to successfully develop an adaptive optics system. So Horace Babcock had come up with a theoretical description of what an adaptive optics system should be, but the technology had not matured to a level where one could design a adaptive optics system back in the 1950s. So then in the 1960s and early 70s, the US military and the US aerospace industry, they put their engineers and scientists to this task of developing an adaptive optics system. And of course, the military's interest in adaptive optics is because you can use it on Earth surveillance satellites, surveillance or spy satellites, because any satellite that is above the Earth's atmosphere, when it is trying to take high resolution images of locations on Earth, it also has to confront with the turbulence of the atmosphere. So the US military put a lot of human resource and research money into developing adaptive optics technology, and the adaptive optics technology got developed in the 1970s. But the astronomy community could not immediately make use of it. That is because since it was a military project, the information was classified. In the 1990s, the US military declassified the design prototype for an adaptive optics system, and once the technology was declassified, it was immediately adopted by the astronomy community to help ground-based telescopes correct for atmospheric aberrations. And with these kind of corrections, earthbound telescopes, observatories on Earth, were able to see almost as clearly as if they were in space. Okay, so I'll now quickly explain what an adaptive optics system is, what are the critical elements of an adaptive optics system. So here is a layout of the adaptive optics system. Okay, adaptive optics system is a back-end instrument on a telescope. That means that it goes behind the telescope. So in this schematic diagram, the telescope is not shown, but instead what is shown is the light that comes from the telescope. Now, the most distinctive components of an adaptive optics system are this adaptive mirror and this wavefront sensor. These are the two most important components of an adaptive optics system. This adaptive mirror is also called a deformable mirror, and it is this adaptive mirror or the deformable mirror which actually makes the optical corrections for wavefronts that are distorted as they pass through the Earth's atmosphere. And the purpose of the wavefront sensor is it measures the turbulence at a rate of hundreds of times a second. The reason why it has to measure these distortions with such a high sampling rate is because the turbulence in the Earth's atmosphere changes once every millisecond or once every few hundreds of milliseconds. Okay, so the turbulence is fast changing in the Earth's atmosphere, and if the turbulence in the atmosphere changes very rapidly, then the distortions that happen to plane parallel wavefronts that come to us from sources at infinity, those distortions will also keep changing with that kind of a time scale of milliseconds. That means that whatever sensors we are using to measure those wavefront distortions have to also respond with a response time of milliseconds or so. Okay, so that's what wavefront sensor does. So the essential idea is as follows. Okay, you have the wavefront coming from the object. Okay, so the telescope collects the light, and this light is sent to this adaptive optics system. Now, if this light has passed through the Earth's atmosphere, then invariably the plane parallel wavefronts will be distorted. Okay. And as these distorted wavefronts fall on the adaptive mirror or deformable mirror, they get reflected, and this reflected light, before it is caught by the detector, which is usually a CCD camera, a high resolution CCD camera, before it is caught by a detector, a part of that light is split using a beam splitter, and it is sent to the wavefront sensor. Now the wavefront sensor senses or measures the wavefront distortion, and it sends that information to a control system. Okay, so this is electronics over here. This control system feeds a set of actuators. Actuators are essentially small, you can think of them as small pistons, which can move up and down based on an input voltage signal that they receive. Okay. So the control system sends a voltage signal to a set of actuators, and based on that, these actuators would move up and down, and this up and down movement will deform the mirror. Now, the shape of the mirror, the deformation of the mirror will happen in such a way that it will be opposite to the distortion that this wavefront is suffering from. So what I mean is, depending on the distortions in the wavefront shape, the deformable mirror's shape is changed such that the light that gets reflected off the mirror once again becomes plane parallel. And the important thing here is this feedback has to happen very fast, okay, so that the response is almost real time. So this is the essence of adaptive optic system, and there is one more component to this adaptive optic system which makes it very, very interesting. For the adaptive optic system to be able to measure the wavefront distortion, it needs a standard source in the plane of the sky against which it can compare the wavefront distortions. So you need a standard source which can be used to measure the amount of wavefront distortion that is happening. And usually astronomers choose a very bright star in the sky as a standard source. But sometimes what happens is the object that you are looking at, it may not have any bright stars in that same field of view. So if it doesn't have any bright field of view, then you don't have any reference star which can be used for measuring the wavefront distortion. So what therefore this adaptive optics system does is, it is equipped with a high power laser, and this high power laser, which is usually a sodium laser, it fires a coherent laser beam into the plane of the sky. And as this laser beam shoots up, okay, when it reaches an altitude of roughly 90 kilometers above sea level, there is a layer of sodium present in the Earth's atmosphere at that altitude. Okay. There are alkali metals which are present in the upper Earth's atmosphere. The sodium is mostly concentrated in a layer that is above the stratosphere at roughly an altitude of 90 kilometers. This laser beam shoots up and it excites the sodium atoms in that upper layer of the Earth's atmosphere. Those excited sodium atoms, they fluoresce, they emit light, and that emitted light creates an artificial star in that plane of the sky. So this kind of a mechanism is called a laser guide star system, and most of the adaptive optic systems that are available at large observatories, they also have this laser guide star system with them. And together, this laser guide star system and the AO system together, it can correct for wavefront distortions, can sense the amount of wavefront distortion and correct for it almost real time. So whatever I just said, I will quickly explain it in this video. I'll just show it in this video. So this is a video from the Gemini Observatory, and it shows the functioning of an adaptive optic system. So here is the telescope. The telescope is located inside a dome. And this is the laser beam being fired into up into the sky. At an altitude of about 90 kilometers, it excites the sodium atoms. The sodium atoms will fluoresce. And as seen from the ground, it looks like an artificial star. So the adaptive optic system is a back-end instrument. Okay, so it goes behind the telescope. So this is the deformable mirror here. And this is a schematic representation of the control system and the wavefront sensor. The wavefront sensor is over here. This is the control system. So when there is no adaptive optics, you can see that the starlight is jittering. It's jumping all over the place. And the adaptive optic system is not switched on. The wavefronts are not plane parallel, they are distorted. Once the adaptive optic system is switched on, the actuators voltage signal goes to the actuators and the deformable mirror changes its shape 1,000 times a second. And as a result, the light that is getting reflected from it once again becomes plane parallel. And you get almost diffraction limited image of point sources in the sky. So I'll just show you some examples of this adaptive optics. I know that I am running out of time, so I'll just take about 5 or 6 minutes more, that's all. So this is a picture of Neptune without adaptive optics and with adaptive optics, and you can see that there's a significant improvement in the angular resolution, the spatial resolution, once you have adaptive optics switched on. Okay. So here is a picture of stars that are close to the galactic center. This particular image is taken at 2.2 micrometer wavelength that corresponds to near infrared. When there is no adaptive optics, you see the stars as blurred images, but once the adaptive optics system is switched on, the image becomes razor sharp. Okay. So once you have such a sharp image, you can clearly identify the positions of stars, and you will be able to measure even tiny displacements in the positions of those stars over time frames of several years, okay, enabling us to measure the movement of these stars. So on to the Nobel Prize discovery. So Reinhard Genzel's group, they were primarily using the VLT, which is the Very Large Telescope, which is located on the Atacama Desert in Chile, in South America. And this one of the VLT telescopes is equipped with the adaptive optics system. So they have been using this telescope in the southern hemisphere, the European Southern Observatory's telescope, for their observations. Andrea Ghez' US group have been using the twin Keck telescopes, which are telescopes located on the summit of a mountain called Mauna Kea in Hawaii. Hawaii is an island of the Pacific Ocean, off the coast of US on the Pacific Ocean. Keck telescopes also have adaptive optic systems built into them now. So these two groups have been using these large telescopes fitted with adaptive optic systems, and they have been carefully monitoring the positions of stars very close to the center of our galaxy. So now I'll show you some of the results from this. Okay. So this is a picture. This is an image. This is a figure taken from Reinhard Genzel's group's 2009 paper, and what you are looking at here is an image of stars which are very close to the galactic center, imaged using the VLT telescope with adaptive optics at near infrared wavelengths. Each black dot that you see here is the position of a star that's very close to the center of the galaxy. And you can see Sagittarius A star marked here. Okay, so this is Sagittarius A star over here. And all the other ones which are marked S1, S2, S3, etc. up to S112, these are all stars which are close to the galactic center. This kind of a sharp image was possible only because VLT telescopes have adaptive optic system built into it. So Reinhard Genzel's group has been measuring the positions of these stars over long periods of time, and they have been able to construct the orbits of these stars, in what orbits these stars have been moving. So here is a reconstruction of the orbits of some of those 112 stars which are close to the galactic center. So here is star S2, S12, S27, all of them. And you can see that all of them are moving in more or less elliptical orbits with a common focus, which is somewhere over here. So by carefully reconstructing these kind of Keplerian orbits, one can find out what is the mass enclosed within these orbits, and the mass that they estimated comes out to be roughly 4.3 into 10 raised to 6 solar mass. So that's roughly 4 million solar mass. So what that means is all these orbits are centered around a point which is enclosing a mass of roughly 4 million solar masses, and they also estimated the distance to the center of our galaxy as 8.3 kiloparsec. Similar set of observations were also done by Andrea Gez's group. So here is a figure from their 2018 paper. Again, what we are looking at are the orbits of individual stars which are close to the galactic center. And that dots represent the positions of those stars as a function of time. So these observations lasted from 1995 to 2020. So that's 25 years of painstaking observations. And it takes that long to be able to collect these many data points to be able to fully map out the trajectory of these stellar orbits. And once again, you can see that all these orbits are closed orbits and with a common focus, elliptical orbits with a common focus. So using Keplerian laws, you can find out what is the mass enclosed within these orbits. And Andrea Guess's group also came up with a mass estimate that's very similar to the European group's estimate, which is roughly 4 million solar mass. And they were able to get accuracy, this resolution accuracies of 100 micro arcsecond, and this kind of an accuracy was possible only because of adaptive optics system being present in these. So what I'm going to show you now is an animation that was published by this UCLA group of Andrea Guess of stars which are orbiting the center of our galaxy. So whatever you see as marked S, these are all stars which are very close to the galactic center. The star here represents the center of our galaxy, and the time is written over here. So 1995.5 means May 1995, okay, the month 5 of 1995. And as this animation plays, you can see how the positions of the stars are changing as a function of time. So of particular interest is the star which they call as S02, because in this 25-year long observations starting from 1995 to 2020, this star S2 has completed nearly 2 or nearly 1 full orbit around the center of our galaxy. You can see this animation once again and focus on star S02, which is this yellow one. When it moves close to the galactic center, you can see that its speed is very high. So the star S02 takes roughly 16 Earth years to go once around the center of our galaxy. It has completed almost 1.5 full orbits around the center. So that many data points means that you can very faithfully reconstruct the Keplerian orbit around it. And when these stars pass close to the galactic center, they acquire speeds which are several thousands of kilometers per second. Which means that they are moving under the influence of a heavy gravitational potential, a strong gravitational potential. So I'm just going to skip some of these slides and I'll just quickly show you what this results further leads to. So now that we know the mass of the supermassive black hole, we can also estimate what the size of its event horizon could be. Okay? Or the Schwarzschild radius could be, and most of you may be knowing these terms, okay, from reading popular literature, etc. So event horizon or Schwarzschild radius corresponds to this boundary around a black hole from within which no information can reach us, not even light. Okay, so this defines the boundary of a black hole, and the Schwarzschild radius is given by this expression 2gm by c square. So if you substitute 4 million solar mass for m and the speed of light in vacuum for c, we can find out what is the size of this supermassive black hole that is present in the center of our galaxy. The size comes out to be 12 million kilometers. Okay, so that is how big this object is in the center of our galaxy. And 12 million kilometers may seem like a huge distance. Okay. But let me remind you that 12 million kilometers is less than the distance of Mercury from the sun. So what that means is you have 4 million solar mass confined to a region that's not bigger than the solar system. That much amount of mass concentrated on such a tiny volume of space, there is only one object that fits that physical description, and that is a black hole. And hence, this is considered as a direct observational evidence for the existence of a supermassive black hole in the heart of our galaxy. Now the question is, can we see the Schwarzschild radius of can we see the boundary or the event horizon or the Schwarzschild radius of this black hole? As it turns out, our current telescopes do not have the angular resolution. Even with adaptive optics, our current telescopes do not have the angular resolution to look at the event horizon of the supermassive black hole in the center of our galaxy. We can easily estimate what is the angular resolution that's needed. All you have to do is convert this 12 million kilometers into an angle in the plane of the sky. We know that the supermassive black hole is at a distance of 8,000 parsec from us. And we know that its size is 12 million kilometers. So we can convert that into an angle. That angle is about 10 micro arcsecond. At infrared wavelengths with adaptive optics, the current accuracy of imaging is of the order of few hundreds of micro arcsecond. So at near infrared wavelengths using adaptive optics, it's not possible to see the event horizon of the supermassive black hole in the center of our galaxy. I'm going to skip a couple of slides because we are running out of time. Okay. There are a lot of observations that are currently going on to study the properties of the supermassive black hole in the center of our galaxy. There are two big questions that looms large about the nature of these supermassive black holes. Firstly, how do these supermassive black holes form? Okay, currently, there is no exact description on what leads to the formation of massive million solar mass or billion solar mass black holes in the centers of galaxies. And also an interesting question that astronomers are actively looking at is, what role do these supermassive black holes play in the evolution of galaxies? Is there any influence that these supermassive black holes have in the way galaxies form and they evolve? So that's the status of the research in this field right now. To sum it up, I'll just say that black holes are perhaps the most mysterious objects in nature. We know that they warp space and time in extreme ways, and they contain what is known as a singularity, which is a mathematically impossible quantity to deal with. The work of Andrea Ghez and Reinhard Genzel and their team of students and postdocs is one of the most convincing evidences of the presence of a black hole in the center of our galaxy. And it's also a great example of how advancements in optical engineering, optics, advancements in technology, and how careful, painstaking observations done with a lot of patience, how all of this can come together to unlock the secrets of the universe and probably shed light on what is arguably the darkest of objects in the universe, which are black holes. So with that, I'll stop my presentation and I'll be happy to take any questions that you may have.
Thank you, Anand sir, for the wonderful lecture. The participants can either unmute and ask questions or leave the questions in the chat box so that we can read it out.
Sir, I have one question. Is there any method to study the radiation coming out from the blue region in the galaxy? You said in the middle there is Sagittarius star, and the blue region you showed in the slide, radiations are coming out from that. So what is the method to study the radiations coming out from that?
Yeah, so the central regions of the galaxy, it's a very persistent source at radio wavelengths, at X-ray wavelengths, at infrared, etc. So if you have a telescope that can focus X-ray photons, if you have a telescope that can focus radio wavelength photons, if you have a telescope that can focus infrared photons, and if you have a detector which can detect those photons, then you can study the intensity of light that is coming from those regions. And so astronomers do that, and they, based on the energy distribution of X-ray photons which are coming from that region, and the energy distribution of radio photons which are coming from that region, the energy distribution tells us that this emission mechanism is synchrotron emission. So synchrotron emission is when charged particles are moving around in the presence of a strong magnetic field. So the radiation seems to be coming from the synchrotron process, and so there is a lot of information that one can gather by carefully analyzing the light that is coming to us from these central regions.
Okay, thank you, sir. And one more question. laser guided star you have shown in that, no, produced by produced by your lab or
Correct. Adaptive optics. Yeah.
So what are the applications of that laser induced laser guided stars which are produced in the atmosphere?
Yeah, so the laser guide star system is an integral part of any adaptive optics system. Okay, so the adaptive optics system needs a reference standard source, preferably a monochromatic source, to be able to sense the wavefront distortions that are coming from that region of the sky. So suppose we are observing a star, a real star, okay, a real star like one of the stars in the center of our galaxy. Then that light from that star is passing through the Earth's atmosphere, and different parts of the atmosphere will have different amounts of turbulence. The turbulence that is in the atmosphere that is directly above our head may not be the same turbulence as the atmosphere that is to one side or towards closer to the horizon. Okay, so ideally, if you are looking at a source that is at a certain patch of the sky, we need to be able to measure the turbulence in that patch of the sky. And to be able to do that, you need a standard star in roughly that same region of the sky where your source is present. Sometimes there will be a very bright star in that region, and the astronomers will use that as the guide star. But often what happens is there won't be any bright star in some regions of the sky. So at that time, this artificial guide star is created by firing a laser beam. Other than that, I don't know of any application that this laser guide star system has, except that it helps the wavefront sensor to measure the distortion that is happening to the wavefront as it passes through the Earth's atmosphere, which is very crucial for the adaptive optics system to function effectively.
Okay, thank you, sir. You have explained everything really well.
There are some questions in the chat box. Should I look at them, or
Sir, Aditya, yes. Sir, Aditya SMS asked, what are the recent studies in black matters?
Black matters or dark matter?
He's typed black matters.
Okay, so dark matter is a completely different entity altogether. Okay, so observations of the last 15-20 years has shown that in addition to normal baryonic matter, okay, baryonic matter means matter which is made of protons and neutrons, ordinary matter, that is what we are all made of. In addition to this baryonic matter, there is a large amount of non-baryonic, non-luminous matter that is present in our universe. And that component is what astronomers refer to as dark matter. So in fact, if you take a representative volume of the universe, okay, some large chunk of the volume of the universe, and if you survey the energy density of material present in that volume, you are likely to find that ordinary matter made of protons and neutrons constitute only 4% of the energy density in that volume. When I say energy density, what I mean is the amount of energy present in a given volume of space. So ordinary matter constitutes only 4%. Vast majority of it, about 20% of it, is made of something called dark matter. Nobody knows what it is. We know that it is non-baryonic in nature, which means that most of the dark matter cannot be made of protons and neutrons. Some of it can be baryonic dark matter, baryonic matter like black holes, neutron stars, etc. But most of it has to be non-baryonic. We know that it doesn't emit any light because we don't see it. And we know that the only way it interacts with ordinary matter, baryonic matter, is via gravitational force. So this is all that people know about dark matter. So if you ask what are the recent advancements in our understanding of dark matter, well, we know that almost every galaxy is surrounded by a huge halo of dark matter, including our own Milky Way galaxy. And it is, in fact, this dark matter halo that provides the gravitational potential for the galaxy to exist as a single entity. And this is true for our Milky Way galaxy. This is true for other galaxies also. In fact, the large-scale structure that we see for our universe is actually baryonic matter tracing dark matter. Okay? So this is now known through very careful observations and through simulations of how dark matter behaves in our universe. We also know how much dark matter is present in our universe, but other than that, there's no clue on what dark matter constitutes. So that's my short answer to that question.
So now Siddharth AV has asked, sir, do India have an AO system?
So no, we do not have any adaptive optics system as yet. Okay, this is a evolving field, and it's also costly to implement an adaptive optics system. So at present, there are no observatories in India which have a adaptive optics system built into it. But in future, maybe there will be.
Abhijit Sharma has asked, sir, can you please tell us something about wormholes and the time traveling associated with it?
Yeah, so wormholes are purely in the realm of theoretical physics. Okay, so there is no observational evidence for the existence of wormhole, but it's an idea that has been there in theoretical astrophysics for quite some time now. So I don't know how to give a comprehensive answer to your question, but I'll just tell you what I understand what wormholes are. So you can think of, if the essential idea of general relativity is that mass can curve space. Okay, so mass curves space, and mass tells space how to curve, and space tells mass how to move. Okay, this is how general relativity is explained in common terms. So if you have a large amount of mass present in a volume of space, there will be a significant curvature to the fabric of space in that region. Now, in the case of a black hole, the mathematical notion called singularity, the theoretical notion called singularity, constitutes a region of space with infinite density, which means that when a black hole is present in the fabric of space, it is almost like a bottomless pit that is present. Now, this idea of wormhole is that we have three-dimensional space. So if we can have two curvatures of space linked together through a fourth dimension, okay, beyond the three spatial dimensions, then you have a pathway to travel between 2 points in space faster than light. Okay. So light would take the shortest path between any 2 points in three-dimensional space, but suppose you come up with a conduit, okay, which connects two regions of space through a dimension that is beyond the third dimension, then you can reach from point A to point B before an electromagnetic signal can reach from point A to point B. So this essentially is the idea of a wormhole. One can describe the properties of a wormhole on a blackboard, but nobody has actually seen any observational evidence for it. This is essentially my answer for it. There are some films that have made use of this idea in a science fiction context.
So Sugat KS has asked, sir, isn't there any other distortions other than the atmosphere when we make an observation of very distant objects like interstellar clouds, etc.?
Yes, Sugat. So there is also distortions that interstellar medium would cause on the incoming light from distant objects. So usually the way that distortion affects our observations is the blue light, okay, light of shorter wavelength, will get easily scattered by the presence of interstellar dust. And so objects will appear redder than what they are. So this is called interstellar reddening. And so objects will appear redder than what they are, and they will appear fainter than what they are. So this can have serious consequences. For example, our estimation of distances is always based on our estimate on how bright an object is and how bright it actually appears to us. So because of interstellar clouds scattering light, if the object appears very faint, then we may estimate a large distance to that object, which could be wrong. So observations of brightnesses of objects have to take into account the extinction of starlight due to the presence of interstellar clouds. So that is something that astronomers are usually very careful about when they interpret data. But those interstellar cloud extinctions are not as severe as the distortions caused by the Earth's atmosphere. The reason is because the Earth's atmosphere is far more denser than any interstellar cloud that you can imagine. Even the densest regions of the interstellar medium are less dense compared to some of the best vacuums that you can produce here on Earth. So interstellar space is really, really empty, and so therefore the distortions or the extinction that happens to starlight is not as severe as the kind of distortions and extinctions that starlight suffer as it passes through the Earth's atmosphere.
So, Sheeja VS asked, Sir, if dark matter around galaxies have gravitational effects, how can we eliminate that effect in the estimation of mass of black holes at the center of galaxy?
Okay, so that's a very good question. Excellent question, Sheeja. So in fact, astronomers are trying very hard to measure the density of dark matter in the central regions of the galaxy, because that aspect has to be factored in when we consider the motion of these hypervelocity stars around the center of our galaxy. So this is something that astronomers are trying very hard to measure. But one thing that we know is that dark matter density is not very high. Okay? The total amount of mass of dark matter present within the galaxy is much more than the baryonic mass that is present in our galaxy. But this dark matter is distributed in a very diffuse form. It's not densely packed together. So for example, within the disk of our galaxy, there is not much dark matter that is present compared to baryonic matter. If there is a lot of dark matter, if a lot of dark matter is present within the disk of our galaxy, then we would easily see its gravitational effects on the planets of the solar system, on the orbits of stars within the galaxy, etc. In fact, we don't find any of that. Okay, so the gravitational effect is there on the large scale of the galaxy, and the amount of dark matter is 10 times more than the amount of visible matter that is present in our galaxy. But this dark matter is distributed in a very diffuse form, which means that it forms a massive halo around the galaxy. So it's not concentrated centrally in our galaxy, and because of that reason, the influence of this dark matter on the motion of stars which are present close to the galactic center, and also its influence on the supermassive black hole, is expected to be minimal. But still, astronomers are interested in finding out what is the extent of that influence, and therefore there's a lot of careful observations now going on to find out the dark matter density in the galactic center.
So we have one more question by Anjana R. Will a black hole hit the Earth?
So the chances of that is slim to none. Okay, I don't think any black hole is going to hit the Earth. So before hitting the Earth, the gravitational influence of the black hole will be felt by objects of the solar system and also by Earth. Okay, so I don't think there is any imminent threat of a black hole hitting the Earth. But we can never say never. Maybe far out into the future, a black hole can drift and enter our solar system. Okay, so that is left to anyone's speculation.
Thank you, sir.
Hello.
Yes, Srihari.
Sir, does the black hole forms at the center of the galaxy, or the galaxy form around the black hole?
Yeah, so this is something that is not very well known. Okay, so what is the seed for the formation of these supermassive black holes? Nobody knows. We know that stars, massive stars, when they live and die, when they explode as supernova, the core of that star can collapse to form a stellar mass black hole, an object with a mass of few times the mass of the sun. So these are small mass black holes, comparatively speaking, small mass black holes. But in the center of our galaxy, we are talking about something that's 1,000,000 times more massive than the sun. So where did these supermassive black holes, how did these supermassive black holes form? Do they form prior to the formation of our galaxy, or do they form along with the formation of our galaxy? These are aspects which are not very well understood. Okay, so unfortunately we cannot go after a direct observation of this, because galaxy formation is a process that has already happened. So in the local universe, you cannot see this phenomenon happening. So the formation of these supermassive black holes is a question for which the answer is yet to be found out, and their role in understanding galaxy formation. So Shija is asking, is it possible that there is a black hole at the center of every galaxy? So yes, observational evidences, there are multiple lines of observational evidences which show that in the center of most galaxies, there is a supermassive black hole that is present. In fact, if you remember, in 2019, April 2019, there was a news item where it gained a lot of media attention. Astronomers had for the very first time imaged the event horizon of a supermassive black hole. I don't know whether you remember this or not, using something called the Event Horizon Telescope. So in the press, it was reported as the first ever image of a black hole. And so this particular image was taken in the center of the event horizon around the supermassive black hole in the center of a galaxy called M87. M87 galaxy is a massive galaxy in the center of a galaxy cluster called the Virgo cluster. So this is a galaxy outside of the Milky Way, and in the center of this galaxy, there is 1 billion solar mass. So that's much more massive than the black hole in the center of our galaxy, 1 billion solar mass supermassive black hole. And the Event Horizon Telescope was used to take a picture of the material surrounding the supermassive black hole in that external galaxy. So, so Meghna is asking, how can we properly study about black hole even though we are not getting any light from it? Yeah, so the only way to study about the existence of black hole is by looking at the gravitational influence of these black holes on neighboring objects. That's the only way to study them. There's another way to study the existence of black holes, which is through a phenomenon called gravitational lensing. Okay, so what happens is the presence of a black hole will warp, will bend, or will cause curvature to space surrounding it. And so if you have an object in the background, and if light is coming from that object, as it passes close to the black hole, because of the warping of space, the light gets bent. Very similar to what happens to light as it passes through a glass lens. So the path of the light beam gets refracted because of the curvature in space created by this black hole, and that results in images of the background objects being formed around the black hole. So this is called gravitational lensing, and by studying the morphology of this lens, one can estimate what is the property of the object which is acting as the lens. So this is another way to study the existence of black holes in our universe. So these are the two only ways. You are right, we don't get any electromagnetic signal from them, so we cannot study them directly.
So Ruxana 789 has asked, can this black hole at the center have some crucial role in the existence of the galaxy as it is?
So Ruxana, if you are asking whether the presence of the supermassive black hole will affect the existence of the solar system in any way, then the answer is no. As far as we are concerned, we are totally unaffected by the presence of the supermassive black hole in the center of our galaxy in any significant way, except that we are studying it. So that is one way in which we are affected by its presence. But we are far displaced from the center of our galaxy. So 8,000 light years is a large distance, and at that distance, the gravitational influence of that black hole is negligible. Okay, almost not there. So there is, except for the stars and gas and dust which is present in the immediate vicinity of the black hole, the rest of the galaxy is totally clueless about the existence of this supermassive black hole in the center.
Thank you, sir. I think that is it. For further queries, I think the email ID of Anand sir will be given so that everyone can clarify their queries. Sir, Siddharth AVS asks, is the solar system revolving around the black hole?
So the entire solar system is going around the center of our galaxy. So that means the sun, all the planets and all other objects that belong to the solar system, we are all orbiting around the center of our galaxy, and we are moving at a speed of about 200 kilometers per second. Okay. with respect to the center of our galaxy. But that is not because of the gravitational influence of the supermassive black hole. It's just that the way the galaxy formed, everything in the galaxy is in orbit around the center of our galaxy. Okay, there is some role of the conservation of angular momentum in it. There's a lot of detail there for me to be able to explain it in 1 or 2 minutes. But to answer your question in simple terms, yes, we are all going around the center of our galaxy at enormously large speeds. But the reason why we don't feel that speed of 200 kilometers, right now we are all moving at 200 kilometers per second speed. The reason why we don't feel that motion is because it's uniform motion. Okay, there is no acceleration or deceleration. And you know that unless there is a change in velocity, there's no way for us to sense motion.
Thank you, sir.